Okay, so can everybody hear me? So the title is a little bit strange because what I will be talking about is work in progress about coming up with some reasonable conjectures about some restriction problem. So, okay. So, in around 2000, Bernd Oerstedt was visiting Cornell, and I was at that time working at basically cohomology of arithmetic groups and so on, and locally symmetric spaces, but cycles and so on were of interest. And so talking with Bernd, we at some point realized, wow, we were interested in a restriction of exactly the same representation of GL4. So we set out, and at that point, I really started working and looking a lot on Toshi's papers. They were really beautiful, but unfortunately, they didn't solve our problem. But I learned a lot in terms of going through them. And they kept really my interest going. And then the next time, which was a remarkable thing, at least for me, was I went to the conference in honor of Thoreau, and Toshi was speaking there. And he was speaking about the restrictions of a representation of OPQ to OP minus Q, P minus 1Q, which has been, this paper and so on has been mentioned here in several talks already. And so, okay, I saw these pictures. Toshi didn't just write down formulas. No, he had some graphic illustration of what happens. And my reaction was, wow, I have seen this before. These pictures, where do they come from? There must be some sort of universal principle around if I see these pictures coming here suddenly by Toshi. And I mean, I had seen them before when I was trying to compute composition series for principal series representations. And there, one usually looks at restrictions to the maximal compact subgroup, and then starting drawing pictures there and parameters of highest weights and so on. They suddenly looked like exactly the stuff Toshi was presenting there. So this thing really stuck with me for a long time. There must be something. And so, in some sense, this lecture here is, well, let's see, can we find some sort of more universal way of rules and things? In that case, for representations not of the orthogonal, but of the unitary groups from UPQ, is what I will be talking about. Okay, so, but of course the general problem, understanding the discrete spectrum of the restriction, is pretty much a hopeless problem if you present it in that generality. But if you get to a sort of more modest thing, well, let's take two sets. You have two groups. Well, take a set of representations of the first group, a set of representations of the second group, and then try to understand the Schramm space. When is it non-zero? Well, of course, understand here means, well, we would like to find a rule. And that's where sort of the difficulty is. I mean, you can do what Bernd Oerstedt and I did. We looked at a particular representation, try to find what the restriction is, but that is far from a rule, and we had no idea how to generalize that. It was way too complicated. We could not, in anything see any way forward. But, well, okay. One can try to do this, but the rule, of course, depends on which sets you pick. mean, if your set is just one representation, then and S2 is all representations, then you end up with your usual restriction problem. But you can sort of change it by looking at a particular subset. So the examples, of course, would be finite dimensional irreducible representations of UN. We take finite dimensional irreducible representations of UN minus 1, and that's a well-known problem. What happens? It's if you look at the highest weights of each of these representations, and you have an interlacing of the highest weights. So that's a really nice rule. Well, there's another version of this. You can take the unitary representations of SON plus 1, 1 with the same infinitesimal character as finite dimensional representations as one set, the same kind of set as S2, but just for this next smaller group. And what you get, again, is actually an interlacing pattern of infinitesimal characters at this time, because you're not in a world where highest weights work, so you have to move to infinitesimal characters. And there's additional things which need to be satisfied. We defined some additional features like height and signature, and so those were additional conditions which needed to be satisfied. But still, it's a nice rule. And that's sort of what I mean by rule. There's a certain set of conditions which need to be satisfied. And they are very precisely defined. Okay. So other examples are, of course, things like the set of holomorphic discrete series representations, and you restrict them to a smaller group, next smaller UPQ, and that goes back to probably around 46 years ago. That was done by Vernier and Jacobson. And in that case, of course, S2 would be all unitary representations, but it turns out the representations which appear only are again holomorphic discrete series representations. So one could just have phrased the thing differently, put an S2 holomorphic discrete series. There are other things like the sets of admissible GK modules, which are usually denoted by AQ lambda. And there is originally this notion goes back to Toshi and the classification, and the actual computations go back to Oshima, I think, to Yoshiki. So again, it's S2 a priori could be anything, but what it turns out in reality is it's another set of AQs, AQ lambdas. And the lambdas satisfy certain interlacing relations. So, or if we look at the minimal unitary representations, that problem has been solved by Toshi together with various collaborators, and that's a finite set of representations, and I think, I never checked completely, but I think the representations which show up in this restriction are again always sort of minimal unitary representations, or very, very small representations. When they're not minimal, they're at least extremely small. So that's an encouraging thing, because if we pick the sets right, there ought to be a rule. Okay, so now the question here is, how do we pick the sets S1, S2, so that things may work right, and what kind of rule can we expect, what invariance and so on. So thinking of this, I looked at various examples. And of course, the first one which came to mind was a paper with Toshi, hidden symmetries of a branching law. And there we looked at the representation, two representations of SO n comma 1 to a smaller SO, and writing it out in the right way, one saw that there was actually some nice rule. All, right, again, it involves the infinitesimal characters of the corresponding groups and interlacing patterns. But the interlacing patterns are different. We took a pair of representations, and there was a sort of nice pattern between what happens for these pair of representations. Okay, so turns out those representations actually are really, one of them is the Flensburg-Jensen representation, and the other one is the representation which has been is an admissible representation, and so it decomposes in a direct sum. Okay. So after that seemed okay. We may want to look at representations which come from different symmetric spaces or generalized symmetric spaces. And, well, what is a rule? I already mentioned rules before involving basically highest weights, infinitesimal characters, and interlacing patterns. But in addition, for most representations, one needed something more. There's something else, some invariants which are needed. So there is a sort of nice way how there was formulation of the restriction for what happens for discrete series of UPQ restricted to UP minus 1Q, which is a whole long volume of Asterix, I think, mostly. And it's formulated very, very general, and it goes back to Gross Prasad and Gan Gross Prasad for the unitary group. And, well, it's complicated because I think it's more than 200 pages, the conjectures in that case, because they should be working over all fields and so on. Now, they were proved in the infinite case by Hongyu He. And he managed to write them down in a very nice, comprehensible way, where you didn't have to go through lots and lots and lots of definitions and things, but he just defined various invariants, which are nice and which you can sort of understand, basically, or at least formally manipulate, let's say that. Now, what are the problems with restrictions of discrete series? The discrete series, you have the Harassandra parameter, which is basically two things, an infinitesimal character and a Weil chamber. And writing out what comes from a restriction, you always have this problem of what to do about the Weil chamber. Because you take a representation, it belongs to one Weil chamber, you look at the restrictions, well, there may be different Weil chambers which appear in the restriction, and so on. So how do you sort of nicely formalize this step here? So that is sort of the big project here if you really want to write it nice. And so, in fact, Hongyu came up with some very easy way of remembering what happens and how to do this. And his rule basically means, okay, instead of looking at your Weil chambers, you look at epsilon characters which are characters from C2 P plus Q. They were introduced by Vaughan to actually really parameterize the discrete series and to even work for L packets and for other things. And so these characters, if they are supposed to parameterize the Weil chambers of UPQ, they have P pluses and Q minuses. Now, this precise way of assigning these things depends on some normalization and so on, but that's basically, that's where it becomes a little bit more tricky. But that's, here I already assumed the normalization, and so that's fine. So an arbitrary sequence, we have P plus Q signs. They have pluses or minuses. And each one of these sequences of pluses and minuses defines a precise Weil chamber and a discrete series, therefore. So that's an easy way. There's a rule of translating this into simple roots and so on. But the basic point is, take these. And so your rule basically involves interlacing conditions for the infinitesimal character, because that's the other thing you need to know if you have a discrete series. And the second information is an interlacing pattern for these little epsilon characters for the different groups. And the conditions which come in is, well, certain interlacing patterns for these epsilon characters are not allowed. Some are allowed, some are not, but there's a clear-cut rule which interlacing patterns are allowed. And you can express your whole restriction of these discrete series by using nothing else but these interlacing patterns and these epsilon characters. So that's, if you want to go anywhere, that's a beautiful way of really try to phrase things. But anything which depends on choices of Weil chambers should be sort of phrased this way, using that idea. Okay. Then the third thing is we have to pick our sets. Now in inspiration 1, I already sort of had a pair of symmetric spaces. But how does one channelize this? Well, what happened here is that Yanis and Akshay looked at spherical spaces. So they defined L groups and so on for the spherical spaces. Our symmetric spaces are definitely spherical spaces, so in that case we have also all the L groups and everything defined. And if we want to do something, well, we may just as well look at all those symmetric spaces which have the same L group. I mean, at least that's one way of going. And so what I will do is I will fix an integer, and then I will take S1, a union of symmetric spaces of this form, where R plus S is equal to K. So we take the union of the discrete series of these symmetric spaces. In my first example for the inspiration, we basically sort of were looking at a case, not completely, but it was similar to taking just R equals 1, and the second space was S equals 1. But it's not quite there because we had not a unitary group, but a spherical, but SO. But that's basically what it comes down to. And, well, that set is well known. You can compute this. And, well, let's go back. So, the regular discrete series, there are limits of discrete series there also, but let's just take the ones with regular infinitesimal character. They are known what they are. They're written down as AQ lambdas. And nice enough, they all are in the same answer packet, no matter which one of these I pick. And that means we have epsilon characters defined by Vogan. And this is Vogan, Barbage, and Trapp, and yeah, I think it's Trappa, this is the last one. So, well, we can write them down. We see them as cohomologically induced from certain parabolics, which we can write down explicitly. And those parabolics are in terms of, again, which we take, are always nicely defined in terms of these epsilon characters. So we can, there's a very nice way of phrasing these things in terms of, again, epsilon characters. It's a little bit more complicated, but at least there are epsilon characters, and the additional nice feature is that, in fact, Meclin and Renard computed exactly what the epsilon characters are for the discrete series representations of each one of these spaces. So they're all in the same answer packet, but not all representations in the answer packet show up as a discrete series of one of these spaces. So it's a subset. So if you want to characterize the subset, again, they have nicely written out the characters, the epsilon characters, and you can find a translation of the epsilon characters into the theta stable parabolics and all of that. But you don't have to write down the parabolics because the epsilon characters contain already this information. So that seems to be, at least I thought this was wrong direction. So the idea now is, okay, there exists another, there ought to be another rule for the restriction in that case, and we are there. Let's see if we can formulate it in similar terms to the rule which, well, and so on, phrased it as interlacing of some pluses and minuses. So that's basically the idea of, well, that's how we want it to go. So, this is pretty much what I explained right now, that why this sort of makes a certain amount of sense to restrict oneself to exactly these subsets. And the nice part here really is Meclin and Renard did all the computations which you may need in the world for. They have exactly the other parameter written out, and every one of these little things exists in their paper about the unitary case. Okay. So now here in this case, what I want to do is I want to consider only what I call a relative branching law. Namely, I assume that the representation of the large group is also in S1 and the representation of the small group is in S2. This is a reasonable restriction, or a lot of a restriction, because if I take an arbitrary representation, there may be many more representations which appear in the restriction, not just the ones which sit in S2. So it really makes, there is a difference if I pick an S2 or if I let S2 just be the whole set of all representations. Okay. So let's look at the equivalent of the case I was stating before for the orthogonal group. And so, for Speh, we worked out the case k equals 1, namely, we took g equals a up cubed, g prime up minus q, to which we want to restrict. And in this kind of game, it is always very important to know how you embed your subgroups. So that's why I specifically write out it fixes this vector EP. We write down our basis vectors so that the inner product for the first P is positive, and from then on it's negative, and I take the EP minus 1. Okay. Then let's take the subgroups H plus and H minus. So here, this H plus is the stabilizer of the first basis vector. Notice this looks, there is another, oops, let's get back. I have a up minus 1q here, and I have a up minus 1q here, and this one here is not the same as this one here. They are not the same subgroups, but they maybe got conjugate. But it depends on the embeddings. So I'm writing these things out carefully. Okay. So we have H plus and H minus, and now we would like to consider the spaces, which I write X plus and X minus, and so here we divide through H plus, here we divide through H minus, and then we take G prime, and the corresponding spaces we get by taking H plus intersecting it with G prime. We get something exactly looking like before. Here we take taking the minus here, and it looks exactly like before. And well, in fact, it is exactly like before as far as the embeddings go. That's why all of this is nicely sort of fixed. Okay. And to just make life easy, let's always assume that P and Q are larger than 3. I think it's enough to have them larger than 2, because if we get smaller, then you have all sorts of additional problems which you can solve, but then it doesn't look as smooth and as clear, because then some of the, well, okay. This is just, it's a technical assumption, and it can be dealt with without it, but then sometimes the restriction of one of the representations we will be considering doesn't contain any discrete spectrum or anything, then you have to rephrase it in a different way. Okay. So it's technical, but it can be avoided, but then the formulation of things is just takes off. Okay. So we look at these discrete series, and they're actually pretty nice because they are, again, homologically induced. And so homologically induced representations, we need a stable parabolic with a Levy, and here are the Levies. So here are two factors here, and here it's u p minus 2, and here it's q minus 2. And so our characters here, well, if we want to get unitary representations, we have to take a trivial character on this factor, and we take unitary characters on each one of these u factors. And so the character we would take L plus on this one here, I'm writing as A plus and A minus, and lambda minus is A minus and is A2 and minus A2. And just to make sure that what I want and I understand is I'm always putting this at the end because of the way how things are. And then I have a few little conditions because I would like this thing to be, if I'm homologically induced, I would like the homologically induced representation to be non-zero, and so on. So that's basically where these conditions sort of come from. Okay, and this one here is precisely, we would like to know for odd and even the AIs. If P plus Q is odd and if P plus Q is even, then this affects if the AIs are half integers or integers. So okay. If we start computing the infinitesimal character, we see that A1 and A2 are equal, and let's write that as A, and then we have two representations, pi, capital Pi plus, capital Pi minus, and they both have the same infinitesimal character. And having the same infinitesimal character is important because otherwise they wouldn't sit in the same L packet and same other packet. We like have an other parameter and all of this. Okay. So, and it's known that these representations appear with multiplicity 1 in L2 of these symmetric spaces. And one of them appears in one of the symmetric spaces, the other one in the other, and that's the only way how they appear. They don't appear in both. Okay. For the small group, it's exactly the same, except that I use a different pi, but the conventions and everything else is the same. Okay. So the other parameters are a homomorphism of the Weyl group cross on SL2C into the L group of UN. The L group of UN is easy because it's just a GL and C. And so that's how our answer packet is defined, which does this. And so, okay. All the representations pi A and pi A plus and pi A minus are in such an answer packet. Okay. Now, how do we get our epsilon characters? Well, what we have to do is we take our homomorphism and we look at the normalizer modulo the centralizer here. In that case, this is a group Z2 squared, and the characters parameterize the representations in the answer packet. And so here is how they are parameterized. So I have epsilon 1 is a plus minus. That would be epsilon plus. Here I have a minus plus. That's my representation pi minus. And of course, I always have to put the A at the bottom if I want to. But generally, this is, for all A's, I have this epsilon. And it really tells me nothing else but that there's a plus or a minus sign on top. I replace that by basically being able to look at the epsilon. So I could write use instead, oops, back. Replace the plus here by an epsilon 1, if I like. I could replace the minus sign here by writing it an epsilon 2 after it, and the same here in small. So I get rid of information about the spaces, but instead I'm putting these little epsilon characters there. Now these precise computations, I'm just following here the notation of Renard and Begler.
You want to write epsilon 1 and 2 prime in the last line, or?
Yes, yes, yes. There's a prime here. Sorry, I overlooked. This is a. So here there should be a prime. It's basically the same, except that I have to, if you notice, what happens here is that the pluses and minuses, so that I see that it's something different. I just use a different way of writing plus and minus. I put an O plus instead of instead of a plus. Because if I look at interlacing patterns, that's the only way you can do this. You can either use colors or something. And this is basically, I keep this notation back at the same as her uses exactly this pluses, these hiding just plus and minus and O plus and O minus. So, okay. Okay, so what we would like to do is now we would like to find pairs of representations pi of the big group and the small group. Both are supposed to be in S1 or respectively S2, and we have a harm between them. So what you see if you write it out here is, well, if we have both plus here, the dimension of the space is 1. And here, this really, did I write it right? Yeah. No, that's wrong. I would like the A to be smaller than the B. Sorry. Yeah, no, okay, here. So if A is larger than B, we get dimension 1, and 0 otherwise, and we get 0 if these plus and minuses are different or if the epsilon characters are different. So that replaces, or in fact generalizes, what you may want to have as work for the infinitesimal characters. You can translate that very quickly, what happens for the infinitesimal characters. I could just add a few numbers, but that's not. Okay. And the second one would be for the minus, and there again we see if these subscripts or the epsilons would be different, we would get 0, and this would be true for all here. And here, if B is larger than A, then we get 1, and otherwise we get 0. So that's basically an interlacing relation. And putting everything together, and rewriting things in the epsilon terms, well, what do we have? We have A and B, and we know that they're even or odd, and so on. And what we can do is the only things, the interlacing patterns between A and B, because one of them is even and one of them is odd. It's not possible for the A and the B to be both integers. One of them is a half integer, the other one is an integer. So we always get a pattern which looks something like this, A minus A, B in the middle. Or we have this interlacing pattern. Okay? So now we want to go from the interlacing pattern to some epsilons. And that here we really follow how the Gross Prasad and Gan Gross Prasad define this, going from interlacing patterns to epsilons. So I have not much time left. So basically, we define these funny epsilons, and we see that if we have interlacing pattern 1, then my epsilon check and epsilon prime check is epsilon 1, and if we have an interlacing pattern 2, then we get the epsilons are all equal to an epsilon 2. That's quickly checked. And so we can actually change this whole theorem by now having epsilons here and phrasing everything here in terms of, well, okay, we have this interlacing pattern. If we have this interlacing pattern, then we get the epsilon 1, epsilon 2, and so this is exactly the same written out as before, just in epsilon 1, epsilon primes. And so we go from interlacing pattern to epsilons. And I can, of course, go backward. If I have these epsilons, I get this interlacing pattern. So the interlacing patterns here really correspond nicely to the different epsilons. That's the whole point of this. That we have interlacing patterns, we get epsilons, and we can also have our epsilon and go back. to an interlacing pattern. And translate our statements of before in exactly this language. That's what the thing is, just translating it. Okay. So now, going back to what we had before, interlacing patterns of our epsilons. Well, we have two epsilons here. I defined, let's go back. Yep. Even further back. Yep. Epsilon 1, I had plus minus. Epsilon 2 was minus plus. And the other one, the same. Okay. So everything here is nothing else but trying to go, figuring out how these things are related. And now, well, the question comes, allowed interlacing patterns between which my epsilon 1 and epsilon 2 are, because a priori I could have any interlacing pattern between these pluses and minuses. But there has to be a restriction because we don't have non-zero intertwining or non-zero harm for everything, but only in very specific cases. So, well, you can define allowed interlacing patterns for the epsilons, for the plus and minuses. And the list here, which I state, is nothing else but the list which Hong Yu has in his paper for the, there's nothing else. It tells you which interlacing patterns are allowed for the restriction of a discrete series. So I'm just taking the same. I'm not inventing any additional thing. I just take the same thing. And, well, we see there are allowed patterns, and there are only two. And that is here, well, we have plus, plus first, and then comes the minuses. That basically means it's epsilon 1 and epsilon 1 prime have to be the same. And here there are two minuses first. Well, okay. That means that I have only the allowed patterns where I have an epsilon 2 should be equal to an epsilon 2 prime. So those are the only allowed patterns, and so we can basically restate everything the same way, and yes. So we get 0 if we don't have an allowed pattern, and if we have an allowed pattern, then we see what I just told, that these two index I and j have to be the same. Allowed patterns really forces us to have I equals j. So there's a subtle interaction between these epsilon factors, or not so subtle, and the basically how the ordering of the epsilon is. Okay, 10 minutes. So, again, this is just continued. If I is unequal to j, then we don't get an allowed pattern. If we don't get an allowed pattern, then the dimension of the space is 0. The thing doesn't show up. Okay, so let's go next. Okay, so we can restate the whole thing in terms of allowed patterns when it's 0, when it's not, and this makes it sort of nice in terms of stating it. And so the whole point here is We didn't prove anything so far. We just translated everything into a pattern and epsilon characters. So how do you prove actually the statements that there is a non-zero restriction? Well, there are two cases. There are the pi plus case and the pi minus case, and they're very different. If I have pi plus, then I have what we call the Flensburg-Jensen representation. Those were discovered 50 years ago, almost 50 years ago, by Flensburg-Jensen, who was the first one who found out what representations appear in these spaces. And this is one of his representations, and, well, you can try. It's nice because he has nice formulas for the functions in the space and the coefficients, and they're beautiful, and they factor, and so you can, in fact, compute nicely period integrals integrating the coefficient of, or the function in the minimal k-type for the large representation against the function in the minimal k-type for a small representation, and you get non-zero if you compute these things out, and so you see basically, well, they appear. That's one way of doing this. And there is another way of doing this, namely, which we also sort of worked out. There are, of course, these representations which I mentioned, this paper of Toshi and these results about restrictions of the orthogonal group and restricting them to various subgroups, which are for fixed point sets of involutions. And, well, that comes in handy. Namely, we start with O 2P 2Q. That contains the O 2P minus 2 2Q, and that contains our U P minus 1Q. Now, on the other side, we can also put immediately a UP and Q and UP minus 1Q here. What we would like to know is this part here. What is possible to obtain, and it's not too difficult, is this. What is the restriction here on that level? It's when the representation, the functions are nice, and you can compute that. And so you know that one, and here you know this restriction, and you can go here to here by just ignoring this one, restricting, taking 0 here, and you take this restriction. And, well, you start with the same representation here, so you have to end up with the same representation here. And that is basically restriction in stages, and you can compute the whole restriction business this way. And then you don't need to work with fancy integrals, but you have to use all the results of Toshi about the restriction. These ones here, this is actually very nicely written out in a paper by Bogen, Schlichtkroll, Bogen, and Trapper. They work all these cases out nicely to see what representations appear there and so on. So one can do this or work out with special functions these integrals. Okay, so next, if we go to the other side, we can use the results of Yoshiki, which he nicely supplied us. It was very nice to give us the list of few results. And, or you can do exactly the same, do this with the restriction in stages, going down. That also gives you the results, what happens as far as restrictions of the big representation of the big group to the small one. Now, if you look through Yoshiki's things, you see there are many more representations which actually appear in the restriction. But we are not interested in those because they are not representations of the symmetry which appear in the L2 of the symmetric spaces. So we can ignore them. And the same kind of thing you have to do. You have to ignore things in this restriction in stages approach. So that's, or you can actually use the techniques which Vargas was telling about by sort of generalizing dual pairs. That also allows you to do exactly the same computations here. So there are 3 ways of working that part out. Okay. So, 3 more minutes. Another example of this is, of course, well, okay. Let's look at the representations here, which are actually G prime admissible. So they should be a direct sum. And, well, the epsilon character in that case is minus, plus, and so on. So we have it here. And what we had in the special case was we just had the first minus and plus, which we just considered in the case k equals 1, the rank 1 case I just looked at. But so, because we know this is always sort of plus minus, it's enough if we want to see what happens. You can modify it and just look at every second term. Because if there's a minus here, I know the next one has to be a plus because of the way how, say, the system works here and the symmetries. So, okay, we just can look at the minuses. And, well, so if we look at the smaller space, again, it looks like minuses. But it looks then like the O minus. It's the same kind of thing. I'm looking at S2. And it doesn't matter if I'm working here with the, here you W and V. And what we are looking at would be, the case where, look at the epsilon characters. And to get to Yoshiki's thing, it would be US. And so in the smaller case, we also have to look. The only thing we don't know yet, so that we can have to look at a UV here. But, well, if I have an epsilon character for the smaller group, it would be a sequence of pluses and minuses. Now I have the rules, the Her rules. And the Her rules would tell me, okay, if they are the right thing, which is not you, but the conjecture is they are, that's math. Well, there is the only way how I could rearrange this is, I think I wrote this, is a sequence like this, up here. This would be the only allowed sequence. The interpretation and our terms would be, the only representations which can appear in the restriction are, again, of the same type as before. They are admissible, and they belong, again, to one of these spaces where let's go back, up, I'm going to the next. It belongs again to one of these spaces where I have here W would be equal to 0 and just V would be equal to K. Okay, so that would be one way of seeing that, at least in that case, again, her rules and all the same rules which we had before work out. And I think I should probably stop, but just, it becomes grammatically more difficult if you look at the rank 2 spaces. And in that case, there are 4 epsilon characters, and you can see very quickly there are 4 representations. 4 AQ lambdas, these are their epsilon characters, and, well, we have the allowed patterns, we have the representations upsale, which you write out, which one can write out, and, well, things get quite tricky for allowed patterns. This is the pattern which we just looked at. In the case of admissible, this one here is a pattern which goes for Fleinstedt-Jensen, and then there are these additional representations which you get. So now I'm running over time, just running the machine forward and seeing what patterns you get. If you use the rules, you get some surprises. Namely, you suddenly end up with some patterns which shouldn't be appealing. But if you look at the pattern of the interlacing patterns here, okay, or here 4 representations, if you look at SP4, well, that has exactly 4 discrete series representations. You can nicely see which of these representations would belong to what discrete series, and people computed those. What happens if I do a restriction of that, and I restrict it to SL2 cross SL2, or SP1 cross SP1? That's done in the early 80s by Kudla and Harris. And, well, the interlacing pattern which shows up is not written, the paper is not written in terms of interlacing patterns and so on, but if you really work it out, then you see they go exactly with what we would get here, following just mechanically the rules. So somewhere there is something strange going on. This shouldn't have had something to do with the discrete series of the symplectic group. We were far away from that, but it appears. And the interlacing patterns are the same. And so what one really has to do is one has to do 2 things. One has to understand why such an interlacing pattern for the symplectic group shows up, because this would be bad news, because you don't know much about the symplectic group and its restrictions. You would much prefer if what would show up would be an orthogonal group SO3-2, and you restrict to SO2-2. So if it's a parity thing, what comes up. So one should just, I didn't check that out. So, but that would be the great hope, because then you can suddenly relate it to the original Gross Prasad conjectures, and you would have had some good idea of what should happen. If it's a symplectic group, forget it. So that's important to check out. And otherwise, well, I just wrote down some interlacing patterns for k equals 2. And I don't know if the representations really decompose the way how I guess they do. I conjecture that's what happens. So one has to really figure out what the restriction here is, and the restriction here is difficult. I didn't find it anywhere, anything related to it in the literature, so it's very difficult. Probably how duality and how pairs is the right way of attacking this, but I don't know. So these are two of the challenges which are difficult to do. Okay, so sorry that I went 5 minutes over.